Hello everyone, this is topic 3 for exam 3, the second major case integrating powers of secants and tangents. To begin with, we'll review an example from Calculus 1 where we have the integral of secant squared 3x times the tangent to the sixth of 3x. Now remember, if it's not fitting a basic 6, then the first place we consider turning to is the integral of u to the n with respect to u. So when we saw case 1 for integrating sines and cosines, our u was the factor that was raised to the power. And then we had the odd power case, and there was a special procedure. So here, considering the same idea, just a basic U-substitution, we have two choices. If we pick u to be secant of 3x, knowing the du needs to be satisfied, its derivative is secant tangent, and it looks like we have way too many tangents. So our only other choice is to pick u to be the tangent of 3x, and if we do, once again knowing that the du needs to be satisfied, the derivative of tangent is secant squared, and there's the factor of secant squared that we need to satisfy our du. So that's our plan. I'll recopy the integral. So it's secant squared 3x tangent to the sixth of 3x with respect to x, and we're going to choose u to be the tangent of 3x. So then our du, secant squared 3x, don't forget times 3, differential dx as well. Routinely modify, we get 1/3 du is secant squared of 3x times the differential dx. Going back to the integral, in an attempt to fit the form of u to the n, we chose u to be tangent, so here we have u to the sixth, and we look at the leftovers, secant squared 3x dx, compare them to our du, and we see that they match. So replace those accordingly. All factors are accounted for, change of variables, bring the 1/3 out in front of the integral of u to the sixth with respect to u, and then we integrate, and we get u to the 7th over 7, the 1/3 tags along of course, and since there's only one u, I'll back substitute that u was tangent of 3x, so tangent to the 7th of 3x plus the constant. So then the question is, what about this example, where we have secant to the 4th and tangent to the 4th? And same idea, but there's a little bit of an issue because we have too many tangents and too many secants to satisfy our du. So this case is very similar to case 1, the odd powers of sines and cosines, for the fact that we're going to force our du to exist again, and then change everything else to be in terms of the u that would produce it. And if secant is even, so this is the even power of secant method, we're going to isolate a secant squared with the dx. And the reason for that is because the derivative of tangent is secant squared. And then we're going to save it, and you can further note that this is going to help to satisfy the du in the formula for the integral of u to the n with respect to u. Then we're going to convert the remaining factors of secants to tangents by the Pythagorean identity. So there's the identity for relating tangents and secants. 1 plus tangent squared is secant squared. And then from there it should be pretty much routine. So once you see an even power of secant, you're going to recopy this. Okay, so we see an even power of secant. We're now going to take two factors away. So we're left with secant squared of 2x. Recopy tangent to the 4th of 2x. The two factors that we borrowed, the secant squared of 2x, push over with the differential dx. Go so far as to box it off and write the word save. And once again, our intent is for this secant squared of 2x to represent the du. So you could look at the cookbook recipe or just simply ask the logical question, if our du is going to be secant squared then what's the trig function whose derivative gives us secant squared? And that would be tangent. So if we could change the remaining factors tangent of secants, to tangents, we'll be able to start the U-substitution process. And we can because, again, we have the identity that 1 plus tangent squared theta is secant squared theta. So basic replacement for secant squared of 2x gives us 1 plus tangent squared of 2x. Recopy tangent to the fourth of 2x, and the secant squared 2x dx that we saved for our du. And now we're ready for a U-substitution because we forced the du to exist and we changed everything else to be in terms of the u that would produce it. That u in particular being the tangent of 2x. Remember, never the power. The power is accommodated in the formula for the integral of u to the n. And from here it should be pretty routine. Derivative tangent, secant squared, same argument 2x, don't forget, times 2, formulate dx as well. Modify 1/2 du is secant squared of 2x times the differential dx. Going back to the integral, u is chosen to be tangent, so here we have 1 plus u squared, u to the fourth, and then the secant squared 2x dx makes up 1/2 du. So we're ready for the change of variables. We'll bring out the 1/2, integral 1 plus u squared, u to the fourth, differential du. And remember, once again, you can only integrate a sum or difference of terms that are of the form u to the n. So we distribute the u to the fourth. So we have 1/2 integral u to the fourth plus u to the sixth, all with respect to u. And now we can integrate. So the way I like to do it, once again, leave the 1/2, open up a set of brackets, integrate term by term. So we get u to the fifth over 5 plus u to the seventh over 7. Get our constant of integration at that point, and distribute the 1/2, so 1/10 u to the fifth plus 1/14 u to the seventh plus your constant. And you could back substitute the tangent for your u, or as we've done in the past, write the little note telling me what u is. So that's the general procedure. We'll see a couple more examples just to firm things up, but hopefully we could take care of that in this one video. And so 2 more examples. First, tangent squared, 5x secant to the 8th. Okay, so secant is even, and I'm going to borrow 2 factors. So recopy tangent squared 5x, taking 2 factors away from secant to the 8th, that's secant to the 6th of 5x. Those 2 factors, secant squared 5x that we borrowed, over with the differential. Box it off, you can write the word save if you like. Okay, and then the logical question once again, look at the cookbook recipe if you need to, but if secant squared, if our intent is for this secant squared to be our du, then we can ask what's the trig function whose derivative is secant squared, and that of course is tangent. So if we could change the remaining factors of secants to tangents, we'll be able to start the U-substitution process. And we can. The basic identity is 1 plus tangent squared is secant squared. And similar to what we've done in the past, if we want secant to the 6th, that's the same as, let me get rid of that, sorry about this. If we want secant to the 6th, that's the same as taking secant squared and cubing it. So if we cube 1 plus tangent squared, that would be the equivalent. Okay, so making that substitution, integral of tangent squared 5x, 1 plus tangent squared 5x represents 2 factors of secant. To account for 6 of them, we'll have to cube it, and then recopy the secant squared 5x dx that we're saving for our du. Okay, U-substitution time. Pick U to be tangent of 5x du secant squared 5x, don't forget, times 5. Differential dx as well. Modifying 1/5 du is secant squared 5x dx. So to the integral, here we have u squared, 1 plus u squared, but as a quantity cubed, and then the secant squared 5x dx makes up 1/5 du. So we'll bring out the 1/5, and we have the integral of u squared, 1 plus u squared now as a quantity cubed, and the differential du. But there's a situation again that makes it a little bit lengthy because we have a binomial cubed. So Pascal's triangle, binomial theorem. Actually, let me take it off to the side. So 1, 1, 1, 1, 2, 1, 1, 3, 3, and 1. So spread them out. 1, 3, 3, and 1. Okay, here all the terms are going to be positive because of the fact that this is a sum of 2 squares under the that's being raised to the power. So there's no way to generate a negative, so everything positive. And we start with the same pattern of the powers. First term 1 to the nth, 3. Second term u squared to the 0. Then decrease and increase. So 1 squared, u squared to the first, 1 to the first, u squared squared, 1 to the 0, and u squared cubed. So we get 1 plus 3 u squared to the first, u squared, plus 3 u squared squared, u to the fourth, and then plus u squared cubed, u to the sixth. Okay, so back to the integral, 1/5 integral. So if you want, we went here, and then back to here. U squared, replace 1 plus u squared cubed by what we just found, and that was 1 plus 3u squared plus 3u to the fourth plus u to the sixth. That's all with respect to u. And now, before we integrate, remember you have to have a sum or difference of terms of the form u to the n. So we'll distribute that u squared. We have 1/5 integral u squared plus 3u to the fourth plus 3u to the sixth plus u to the eighth, all with respect to u. Finally, we can integrate. 1/5, some brackets, u cubed over 3 plus 3 tags along, u to the 5th over 5 plus 3 tags along, u to the 7th over 7, and plus u to the 9th over 9. Close up the brackets, add our constant, and finally finish it up. Distribute the 1/5. So 1/15 u cubed plus 3 over 25 u to the 5th plus 3 over 35 u to the 7th, and plus 1 over 45 u to the 9th, plus our constant, and this is where u is equal to, was tangent of 5x. Okay, so probably should have given myself a little more room there, but I think that works. And the final example for this topic is secant all along, secant to the 10th. But as long as the power on secant is even, you can handle it. Because, again, it's like we're reversing the U-Substitution process. If we take two factors away from secant to the 10th, we're left with secant to the 8th. And those two factors, we want that to represent our du. So we write the word save. Logical question, once again, we could ask, okay, this is the 8th power here, is if secant squared is the du, what's the u that gives us secant squared, or whose derivative is secant squared, and that would be tangent. So therefore, if we could change these to tangents, we'll be able to start the U-Substitution process. And once again, the identity off to the side here, 1 plus tangent squared theta is secant squared of theta. And so if I want 8 factors of secant, that would be the same as taking secant squared and raising it to the 4th power. And that would give secant to the 8th. And so that's equivalent to taking 1 plus tangent squared theta and raising it to the 4th. So that's our next move. 1 plus tangent squared of 3x accounts for 2 factors of secant of 3x, but to account for 8 factors, again, to the 4th. And then the secant squared of 3x dx that we're saving for our du. And now is the time we can make a change of variables, because we've forced our du to exist in the form of the secant squared of 3x, and we changed everything else to be in terms of the u that produces it, in particular that u is the tangent of 3x. Again, never the power. Power is accommodated in the formula for the integral of u to the n. Derivative of tangent, secant squared 3x, don't forget times 3, differential dx as well. Routinely modify, 1/3 du, secant squared of 3x times the differential dx. Going back to the integral, we have 1 plus u squared, but now as a quantity to the 4th. And then the secant squared 3x dx makes up 1/3 du. So every factor is accounted for. Change of variables, 1/3 integral, 1 plus u squared, now as a quantity to the 4th with respect to u. And I'm going to draw a little wavy line again because I see a binomial to a power 3 or greater. So Pascal, once again, got enough room to do it, I think, here with the little wavy line. You don't have to generate the triangle every time. Spread out the coefficients, 1, 4, 6, 4, and 1. And again, you have 2 choices, either all positive or they alternate in terms of the signs of the terms in the expansion. And if it's a sum in the binomial, they're all positive. And then we start with our pattern of powers. So 1 is the first term to the 4th, u squared to the 0, decrease 1 cubed, increase u squared to the 1st, decrease 1 squared, u squared squared, 1 to the 1st, u squared cubed, finally 1 to the 0, and u squared to the 4th. So that gives us, okay, everything's a 1. Again, what comes out of this is really just the coefficients. As as the powers on u. So we've got 1 plus 4 u squared to the first, u squared, plus 6 u squared squared, u to the fourth, plus 4 u squared cubed, u to the sixth, and then finally plus u to the squared to the fourth, which is u to the eighth. So a little wavy line going back to the integration. And third integral, okay, replace the 1 plus u squared to the fourth by what we just found. 1 plus 4u squared plus 6u to the fourth plus 4u to the sixth plus u to the eighth. It's all with respect to u. And here's an instance where typically in the examples we've seen in the past, we had to distribute before we could integrate. But here everything is, there's no factor, like if there were u squared or u cubed out in front or trailing off behind, we'd have to distribute that first. But here we're ready to integrate. So I'll recopy the 1/3. Okay, be careful here. Integrating 1 with respect to u, we get u. And then plus 4, and continuing u cubed over 3, plus 6, u to the fifth over 5, plus 4, to the seventh over 7, and then plus u to the ninth over 9, close up the brackets, add the constant, and finally distribute the 1/3, so 1/3 u plus 4/9 u cubed. 3 goes into 6 twice, so 2/5 u to the fifth, plus 4 over 21 u to the seventh, plus 1 over 27 u to the ninth, plus c. And obviously a case where it's most convenient just to write the little note telling us what u was. In this case, tangent of 3x. Okay, so that's the end for this topic, and we'll see you in the next topic.